Good day. My SURF students are contributing to a multi-year project aimed at developing quantitative techniques to identify a bat species using only a recording of its search phase echolocation calls. Santa Rosa Island and its changing ecology was an initial motivation for this project. Last year, my SURF bat team did work that allowed us to apply for and receive a National Park Service permit to place long-term passive detectors on Santa Rosa Island. Last year, these students traveled to Santa Rosa Island, placed detectors, gathered data, and analyzed that data. Our goal this year was to continue that work.
We were set to contribute to this multi-year project when COVID-19 happened. The pandemic made many parts of this project impossible, including collecting data on Santa Rosa Island, the Los Padres Wilderness, or on campus, or even meeting up as a group to learn how to use the Anabat Insight detector.
Since bats are everywhere, we decided to use quantitative data analysis to identify the bat species in our own backyards. Though the best way to identify a bat is through its physical characteristics, it isn't always possible to do that. A bat's echolocation calls can be recorded and visualized with various technology and softwares. We each placed detectors that Dr. Miller lent us in our yards. The detectors were placed in different locations. One detector was placed in Simi Valley, California, in a backyard with various plants and trees. There was also a golf course across the street which resulted in high bat activity. The second detector was placed in a backyard in Camarillo, California with various trees and plants around. The third and final detector was placed on a balcony in an apartment complex in Camarillo, California. The microphone was faced away from the buildings towards trees. We recorded bat calls sunset to sunrise daily for a few weeks. Once we had accumulated 800 calls each, we sorted the calls and generated reports through Anabat Insight. Those reports were then imported to MATLAB and RStudio for analysis. We also used Google Sheets to compare our statistics and compare our work. We wrote papers that conveyed our findings and our understanding through Overleaf and Google Docs.
Bats use echolocation to get a better sense of their surroundings, and in this process, they create ultrasonic chirps that humans can't hear, but the bat detectors that we set up could record. Using Anabat Insight, we were able to create visualizations of our recorded bat calls, as well as multi-dimensional data sets, which represented several different aspects of our calls. These included parameters such as maximum frequency, minimum frequency, average frequency, call duration, and length of time between calls. This allowed the team to learn about the different quantitative methods that are used for identifying bat species. Using Anabat Insight, we identified call recordings which contained search phase echolocation calls, which are calls produced by the bat when they're foraging for insects. Then, we learned how to identify different bat species by their calls.
Everyone is familiar with the idea that birds can be identified by their bird songs. However, bats are not birds. Unlike bird songs, which are often complex and are used by the birds to identify themselves, bat chirps are fairly simple and are used for a different purpose. The chirps are either constant frequency as seen in the first picture, frequency modulated as seen in the second picture, or a mix of both. Now, what chirp a bat uses in order for echolocation depends on what type of habitat it is foraging through. For example, a bat, such as a hoary bat that would be flying over an open field, would use a constant frequency call because the sound waves travel further and can come back. A bat searching through a highly cluttered environment, such as a dense forest, would use a frequency modulated call. To figure out which species we were recording, we first looked up the species that were native to Southern California. We then used the CI Libraries database to look through peer-reviewed articles and other sources to see what these echolocation calls looked like. We compared the echolocation calls in the literature to the echolocation calls we recorded on Anabat Insight. Based on this, we concluded that we had recorded silver-haired bats, hoary bats, and canyon bats.
Once we made educated guesses as to what species we had recorded, we used MATLAB and RStudio to create visual representations to see how accurate our guesses were and how our data compared. For example, we were able to make a classification model based on linear discriminant function analysis. To do this, we used five-fold validation to split our data into 5 subsets. One subset became the training set and built the model, and the other 4 subsets tested and validated the model. Once we had each created a model, we tested each other's data to see how the classifications compared in the form of a confusion matrix. We also created boxplots to evaluate how our guesses compared to one another by parameter, species, and technician. For the species, LACI is the hoary bat, LANO is the silver-haired bat, and PAHE is the canyon bat. As you can see by the matrix with Sergio's data and Jessica's model, the classifications did not match. The box plot also shows misclassifications among our maximum frequencies. These inconsistencies were made by cleaning the calls differently. We came together and discussed how we clean the calls, and once we had adapted a way for all of us to clean the calls, we continued on.
Once we agreed on a method for cleaning all of our calls, we used our new knowledge to create smaller subsets of our data, which we used to create a new classification model. Our new classification model was much more accurate at not only identifying our own recorded calls, but those recorded by our teammates. Looking at our old matrices, you can see that there's much more red, which means there's more misidentification of our calls. Looking at the new model, our confusion matrix shows much more accurate species identification on the main diagonal. Although this shows much more accuracy in classification, we don't see the same results in our box plots. When comparing box plots, we want the patterns between our set of box plots for each technician to match. For example, in the set of red box plots in the before set, we can see that each species has an increasing F maximum. In the green set, we see that it decreases before increasing, and in the blue set, we see that it increases before decreasing. In our new classification model, we can see that there's more agreement between each technician set of box plots. However, they still do not match exactly. This means that there's still much to improve on in our classification models and our data sets. As of today, we are still working on fine-tuning our data sets such that they can be used beyond our own sets of data.
After SURF, we plan to continue this work in the fall. We want to use the skills we have learned this summer to work with data that Dr. Miller has already gathered from the island. We plan to repeat the process of cleaning calls, creating models, box plots, and confusion matrices to identify bats that have been recorded on Santa Rosa Island. And hopefully, after the pandemic, return to Santa Rosa Island to record our own.